delay. So there was a little confusion because there are two ways to find those equilibria. The first way is something which uses the properties of zero-sum games. The other way is good for any mixed extension of a finite game. So in the case of a zero-sum game, we know that we can just take the max min and min max. Those are the equilibria. So what is the max min for the first player? So we look at the value of the first player, the utility of the first player, and then the second player minimizes the first player's utility as much as possible. So when the first player chooses P, the second player can choose either the first or the second column, or the mixin. So if the second player chooses one column, this is the value of the first player, depending on the P, it's function 2P minus 1. If the first player chooses another, if the second player chooses another column, this is what the first player gets based again on her P. So given a P, the minimum that the second player can give the first player, so the worst situation that the second player can inflict on the first player, is denoted by the pink color here. And the first player chooses P so as to maximize this pink graph. So the first player needs to look for this point of intersection. And that's exactly when one line intersects with the other one. That's exactly what we see here. So that's the max min of the first player. That's the P that the first player chooses. And now, as for the second player, similarly. So given the first player chooses one column, that's the utility the second player gets based on the Q. Given that the first player chooses another column, another row, the row player chooses another row. That's the utility that the second player gets based on the Q that she chooses. And since the second player is a column player, maximizes her utility given that the first player tries to minimize. So this is the minimum that the first player can inflict upon the second. And the maximizing that the second player does looks for this intersection, and that's exactly what the first what it means. So the column player has to choose this Q. So this approach uses this fact that we can look that the equilibria are exactly the max means of the players. Those are the equilibrium strategy. So we were looking for the max means. Now so we can approach this in the following manner. We proved on the previous lesson that in any game, a mixed strategy is a Nash equilibrium if and only if each strategy in the support is a best response. And that's what we are going to use here. So here we are going to have to look for the possible mixed Nash equilibria, not depending on the fact that it's a zero-sum game. So first, no pure equilibrium exists. We already said this. Then maybe there is an equilibrium where one player plays purely, the other one plays not purely. No, because if one player plays purely, then the other one has to react purely. So let's say if the row player chooses high taxes, then the column player, the best response would be choosing not publish. If the column player chooses low taxes, then the best response of the column player would be publish. And the similar logic applies in the outcome. So if the column player chooses to publish, then the row player chooses high taxes because 1 is better than -1, and if the column player chooses not publish, then the row player chooses low taxes because 1 is better than -2. So if at least one player is pure, then the other one is also pure, and this, as we already said, is never in Nash equilibrium in this case. So we only are left with the fully mixed options when nobody plays a deterministic strategy, and here we know there should be an equilibrium from the theorem of Nash. So let us look for such an equilibrium. So each player has to get the same value from both strategies because they are both in the support, since it's a fully mixed equilibrium. So they have to be both responses. So each pair has to have equal values for both strategies. What does it mean? It means that the column player has to have the same value from publishing and non-publishing. Now, when the row player plays high with probability P and low with probability 1 minus P, the column player gets the following value from publishing. It's minus 1 times P plus 1 times minus P. 1 minus P. This. And this has to be equal that the column player gets from the second option, which is 2 times P minus 1 times 1 minus P. And this is equal. And as for the other condition is that the mixing of the column players to be such that for the row player, both rows are the same. So Q has to be such that the high taxes give the same as low taxes, which means that 1 times P plus minus 2 times, 1 times Q plus minus 2 times 1 minus Q gives the same value as minus 1 times Q plus 1 times minus Q. And those two conditions can be immediately checked to be equivalent to what we got before when we looked at this game using that the equilibria has to be max means of the corresponding players. So okay, so in this case we've seen that indeed there are several options because it's a constant sum game. So in addition to the normal way to look for mixed equilibria, we also have this way which uses the fact that it's a zero-sum game. Now let's look at another example. And here it's a bit in a different example because here we do have a pure equilibrium. It's AC, so the first player chooses A, the second player chooses C. It's another game. Here we have this pure equilibrium. Now, what are the mixed Nash equilibrium? So as we know, all the pure equilibrium are also mixed, but maybe there are more mixed Nash equilibrium. Okay. So let us look for other mixed Nash equilibrium, not pure. So since the strategy is dominated, maybe we can delete it, but no, it's weakly dominated. Because if the column player chooses D, it's strictly worse than A, but if the column player chooses C, it's equivalent to A. So it's weakly dominated, therefore we cannot just delete it. It would not change the value, but it can remove strategies which are equilibrium strategies. So we need to stay with the matrix as is and look for the equilibrium in another way. So let us look for the equilibrium another way. So if player 1 plays a pure strategy, then 2 has to best respond purely, because if player 1 plays A, then 2 has to choose C because -1 is better than -2. If player 1 plays B, then 2 has to choose D because 0 is better than -1. And so if player 1 plays purely, then player 2 has to best respond purely, and that's going to be something which is pure, and for pure equilibrium we have already found all the options. It's A, C. So that's not interesting. So let us look at the other option when player 2 plays purely. Now here it can be that if player 2 plays C, then player 1 can play both A and B. It gets the same value for both. And therefore it can arbitrarily mix from his point of view between those strategies A and B. So P and -P. So the only condition when player 1 mixes is that player 2 can choose both of her strategies with equal probability. Excuse me. That player 2 gets the same from both strategies, from C and D. Because if not, if player 2 has to play only one strategy, actually, okay, no. The player 1 can indeed mix from her point of view anyhow, and for having an equilibrium, we need that mixing P and -P to be such that player 2 will have a reason to choose C, because that's what we assume, that player 2 chooses a pure strategy. So it means that basically when player 2 chooses C, she gets at least what she gets for choosing D. So -1 times P minus 1 times 1 minus P, that's for choosing C, it's at least -2 times P plus 0 for choosing D. And that is equivalent to P being at least half. So if player 2 chooses C, then player 1 randomizes, and that is something which allows us to have this pure mixed equilibrium. And if player 2 chooses D, then player 1 may not randomize, because 2 is strictly better than 0. So then we would get again a pure equilibrium, and we already have dealt with that. So the only pure mixed equilibrium is that player 1 randomizes with any P at least half, and player 2 chooses C. And the final option is, let us try to find fully mixed profile, so that player 1 has P 1 minus P, and player 2 randomizes between C and D with probabilities Q and 1 minus Q. And here, by the lemma, we know that a profile is an equilibrium if and only if each strategy is in support. And here all the strategies are in support because we assume it's fully mixed. Each strategy in support is the best response. So we have to require that both strategies will be equally profitable for both players. And that means basically that P is such that for the second player, C and D are the same. So that -1 times P minus 1 times 1 minus P, that's for C, is equal to the utility that the second player gets for choosing D, which is -2 times P plus 0. And for player 1, A and B have to be the same, so that Q is such that when player 1 chooses A and gets 1 times Q plus 2 times 1 minus Q, is equal to what player 1 gets when she chooses B, and gets 1 times Q and plus 0. But that's one of the half-mixed profiles we have already seen, so that's not something new. And therefore the answer is, let us remind you what we did. We found that there is this profile which is pure, which is in equilibrium AC, and also when player 1 randomizes, there's probability at least half for A, and player 2 chooses C, that's also an equilibrium, so it includes in particular the deterministic choice of A and C, and these are all the equilibria. So all the equilibria are P for player 1 with probability at least half, and C for player 2 with probability 1. Please notice that here we have not used the fact that the game is zero-sum game. We have just used the fact that it's just a finite game, and we looked at all the mixed Nash equilibria. So we also could look at this game using the fact that it's a zero-sum game, but we have not done that.